Our last lesson is on applications of sinusoidal functions. So now that we know how to determine the function from a graph, now that we know how to write the equation of a function, of a cos or a sine graph, now we're going to see how do we apply it to real-world situations. So the first example is a nail caught in the tread of a rotating tire at point N. And you can see how they have represented that situation because a tire rotating around and around and around the circle is just represented by a sine graph. You can tell that this is a sine graph because it starts at where would be your midline, right through there. And you can see that it is going from there up to its maximum point, down to its minimum point, and that would be one period of that sine function. Okay? Anything like this that happens with a tire rotating or a Ferris wheel rotating or the waves of the tide coming in at regular intervals, anything like that that happens on a regular interval is a periodic or can be modeled with a periodic function because that's something that repeats at regular intervals over and over and over again. Okay? So as the tire rotates, the path traced out by the nail can be represented by this sine function. The points A, B, A and C are maximum point and a minimum point of this function. And the points N, B, and D, as you can see, they lie right on that midline, right? Right here, and right here. Okay, so Jake and Jill were given the following information and asked to determine the height of the nail after 6.5 seconds. Okay, well, let's just think about that for a minute. First, in order to be able to determine some of these details and to be able to mark them in the graph, we're going to have to be able to figure out what the period is of this graph, what the amplitude of this graph is, and other details like that. So let's see. We know that the tire has a diameter of 50 centimeters. So what that means is from this maximum point right to the minimum point, this whole thing is 50 centimeters. Well, if that's 50 centimeters, then what would be my amplitude? This is my midline running right through the middle, right? So obviously my amplitude is going to be half of that. So we know right away our amplitude is 25 centimeters. Okay? We also know the tire rotates at 10 revolutions a minute. Okay? Now remember, one revolution is this complete sine function one time. So one revolution is what we need to figure out because that will be the period of this function. Okay? So we can just make a simple comparison. If we know that there's 10 revolutions in 1 minute, 1 minute is 60 seconds, so 10 revolutions in 60 seconds, then we want to know one revolution or one complete period of this sine function will happen in, well, what did we have to do on the top? To get from 10 to 1, we had to divide by 10. So on the bottom, you're going to do the same thing, divide by 10. 60 divided by 10 is 6. Okay, so it does one revolution every 6 seconds. Okay, 10 revolutions in 60 seconds. Makes sense, right? Okay, so that gives us our period because one revolution of that tire all the way around is one period of the function. So that means our period is 6 seconds. It takes 6 seconds to do one complete revolution. After 1.5 seconds, the nail has reached its maximum height. That's what we see here in A. So we can mark this on our scale. That would be 1.5 seconds because it tells us our x-axis here is the time in seconds. Okay? And it says after 4.5 seconds, the nail touches the ground. So this must be 4.5 seconds right there. Okay? Well, we've just determined that the complete period of this function is 6 seconds. So to go from start point to its maximum, down to its minimum, and back to its start point again, that is 6 seconds. So we can mark that on our scale as well. Well, what is our scale going up by then? How did we get from 4.5 to 6? That's every 1.5 seconds, right? So if this is time 0, this is 1.5. What's this missing one in the middle here? Add another 1.5. 3 seconds, 4.5 seconds, 6 seconds. This would be 7.5 seconds. This will be 9 seconds. This will be 10.5. And this will be 12 seconds right here. Okay? And that makes sense because that's another whole period of this function, right? Okay? So if the period of the function is 6 seconds, it takes 6 seconds to do one complete period, one complete rotation of this tire, then it makes sense that it would take 12 seconds to do 2 complete rotations of that tire, right? Okay, so the two boys, Jake and Jill, have tried this different ways, okay? Jake's method, he used the information written or given to write a scale for each axis, okay? And he marked 4.5 at point C. Why did he mark 4.5 at point C? How did he know that this value would be 4.5? Well, he obviously had to figure out the scale on this x-axis, right? He had to figure out what each one of these distances is on the x-axis, okay? If he knew that he had figured out that the period was 6 seconds, okay, then he can divide that period into 1, 2, 3, 4 equal parts, right? So he did what we've been doing lately to figure out our scale on the x-axis. He took what he knew, that's 6, and he divided it into 4 equal parts. And when he did that, he got an answer of 1.5, or 3/2, which is the same thing as 1.5. So what that tells him is, so each mark represents 1.5 seconds. Okay? So then it says write numbers at the scale marks. We've already done that. Determine the amplitude, the period, and the midline value for this graph. Okay? Well, I guess that makes it too small. Let's keep it enlarged. You may have to just scroll up and down, okay? So the amplitude, well, we've already determined that if the diameter of this whole wheel from top to bottom is 50 centimeters, then our amplitude is half of that. So amplitude was 25. Okay, the period we've already calculated right here. Period was 6 seconds. And we need to figure out our midline. Well, we know the midline is marked right on here. The midline runs right through the middle, right? So right here, that's our midline. If the whole height is 50, our midline is in the middle. Obviously, the midline is at 25. So it asks us to determine the equation for the height of the nail as a function of time in the form where height, dependent on the time, is a sine bt plus d. We have been identifying a, b, and d values, and so this will be really easy just to plug them all in. So the height as a function of time equals the amplitude, 25, sine. Our b value, we haven't calculated our b value. We know our period, but that is not our b value. So we have to use our formula. So b equals 2 pi over our period, and our period is 6. So b is 1/3 pi, or pi over 3, right? So we can come back to our equation and put that in. Pi over 3 is our b value times t. And then we have no c. And we have a d value, which is our vertical displacement. That's our midline. And it's positive 25, so plus 25. That would be the equation. And you could write it either in radian form like it is here when we used 2 pi over 6 to figure out our b, or we could have done it in degree form. In that case, it would have been b equals, instead of 2 pi, we would have put 360 over 6, and that would have been 60. That's measuring in degrees, okay? So then in this case, instead of this pi over 3 here, this would have said 60t, okay? But it will be the exact same equation otherwise. How far to the nearest tenth of a centimeter is the nail above the ground after 6.5 seconds? Okay, so let's go to our graph and just have a look at what that's asking. After 6.5 seconds, so that would be right in here, we want to know how high that nail is, so what this point is on the graph. Okay, so how can we figure that out? This 6.5 here, that's on our x, right? That's our x-axis. And so we want to know a value on this graph here at this point when our x is 6.5. So we can just plug that right into our calculator once we've put this equation in, into our y1. Then we're going to go second, calculate a value when x is 6.5. And if you plug that in, you'll have to put the equation in first. Plug this in. It will tell you that your y is 37.5. And that's a measurement of height. Y is your vertical distance. It tells us that that scale is measuring in centimeters. So 37.5 centimeters above the ground. Okay, so this is what is meant by applications of sinusoidal functions. It's where we can model some event that happens over regular periods, so it's a periodic event. It happens over and over and over again. So we can model it with either a sine or a cos graph. And now that we know so much about sine and cos graphs, we can use what we know to allow us to come up with the equation for it, and then to be able to answer questions like question D, using our calculator to determine that amount. Or I suppose we could have plugged in this x into our x here. Remember, our x-axis is the time, so that we're modeling the t for time, but it really means your x value. We could have put 6.5 in there and figured it out algebraically as well. But your calculator will do it for you. So most likely you'll do it that way most of the time. Okay, so this is how Jake attempted to solve this problem. But his friend Gilles did it a different way. Gilles decided that he could use the data points, that N, A, B, C, D that were marked on that picture, and he could use that data then to perform a sinusoidal regression to determine the equation for the height, instead of having to calculate it. And so he looked back at the diagram and he said, okay, I've got a lot written on here, so I'm just going to erase this so we'll be able to see those points. And he said, okay, what is my, at point N, right here, what would be my x value and what would be my y value? And so that would be over 0 and up. Well, if this whole distance is 50, then this distance halfway is up 25, right? And so that's what he's put in here. This is your x, this is your y, right? So his x was over 0 and up 25. So then he looked at A and he said, well, what would be the coordinates of that spot? Over 1.5 and up 50, right? And so that's what he put in as his x and his y. Over 1.5 and up 50. Then he did the same thing with B, and B is over 3 and up 25. And then he did the same with C. C is over 4.5 and up 0. And D is over 6 and up 25. Okay? Then you just take that set of data and perform a sinusoidal regression on the data. Okay, and that looks like this, sine reg on your calculator. So I'll just show you that really quickly on mine. Okay, so if you remember, you go into Stat, okay, you want to Edit, and if you already have something in those columns, remember you go up here to the top band at the very top, and you hit Clear and Enter, and it will clear out that whole column, okay? So you would just put those data points in. You do it on your calculator while I do it on mine. And then, like I've said before, just be sure that you double check and make sure you haven't made any mistakes once you enter the data, okay? Because it is really easy to make a mistake and it would throw off your whole calculation, okay? Then remember you go into Stat. Well, let's go out of this, I guess. Go into Stat, ask it to calculate, and if you scroll down through this list, you will see our linear regression, quadratic regressions, cubic regressions, the ones we've been used to doing. And if you keep going down through this list, you'll see a linear regression, number 8, in the format of a regular linear equation. This ln, that's the natural log regression. Then you can do an exponential regression, a power regression, and if you keep going, finally down here at the very bottom, ABC, you'll see that C is your sine regression. And then you'll hit Enter, and just hit Enter until it calculates it for you. And you'll see that the equation, the format of the equation is A times sine bx plus c plus d, which is what we're used to seeing. It gives us our A value, our B value, we have no C value, and our D value, okay? And so then he would just write, okay, the height as a function of time is, his A is 25, sine, bracket, his B is 1.05 if you round it to the nearest hundredth, which is what the question asked us to do. And that's times x, or t in this case, because our x-axis is our time, and plus 25. Which is exactly the same thing that his friend Jake got the exact same equation when he did it. Okay, and then we have a question that says, how far to the nearest tenth of a centimeter is the nail above the ground after 6.5 seconds? So again, we need to get our calculator to actually graph this equation. Right now, if you went in and asked it to graph, you, at this point, have not put that equation into your y1. So you have to do that first before it will graph it. So go second and quit. Or clear, I guess, to get out of there. If you go to y1, you have to make sure if you have any previous equation in there that you've cleared that out. And you have to tell it to take that equation. Do you remember how to do that? Which key it is? You go to your vars key. You go down to number 5, statistics. Go across to the top where it says equation, and you want it to take the regression equation, number 1. It will put that equation in there for you, and then it will graph it. You'll need to make sure your windows are set though, and we know that our windows have to be, well, if we have an amplitude of 25, okay, so a normal sine graph starts at 0, right? But we have an amplitude of 25, that means our max and min points would be at negative 25 and positive 25, but we have vertically translated this graph 25 units up. So that means our minimum is now going to be at 0. Our maximum is going to be at 50. Okay? And that's our minimum and maximum on our y. Okay? So we're going to have to set our y's for from 0 to 50. And maybe going up, since that's pretty big jumps, let's go up by 5s instead of by 1s. And then for your x's, how do you know how far you go on your x's? Well, you can look at your data and you can see, you could have looked on your data, I guess, for your y values as well. Your data goes from 0 to 6. And it might be a good idea to go a little bit below and a little bit above. So maybe let's go -5, and then instead of 6, we'll go up to 10. Maybe we should do that as well on our y max and min. Instead of going just to 50, which is our max, let's go to 60 instead. And same with our min value. Instead of 0, let's go just a little below that, -5. Okay, and then we'll be able to see it. If you ever hit graph and you've put all of this in, either an equation like this or a set of data like this, and you're expecting it to be a sine or a cos graph, and you get just a straight line straight across the page, all that means is that you're in the wrong mode, and you just need to change your mode, okay? But in this case, we're getting what we expected to see, okay? You can see that it is a sine graph. It's starting high, though, at a y value of 25, and it's going up and then down to its minimum of 0. Okay, so well, when I say it's starting high, I mean it's starting at its midline, right? At the midline at 25, and it's going up from there to its maximum point and then down to its minimum point, okay, of 0. Okay, so we're seeing exactly what we wanted to see. So now that we have it in our calculator, we can answer C, which is how far to the nearest tenth of a centimeter is the nail above the ground after 6.5 seconds. So again, we want to know on our x scale, that's the time, when x is 6.5, what is the y? Y is your height, how high above the ground it is. So again, that's just second, and we're going to calculate. We're going to calculate a value when x is 6.5. And we should expect to get the exact same answer we got on the previous page when we did this, and it tells us that when x is 6.5, our y is 37.5, which is the exact same thing we got when we did it by hand. Okay, so second, calculate what? A value when x is 6.5. And it'll tell you y is 37.5 at that point. And that's a vertical distance of, centimeters. Okay. The note at the bottom of your page just says, in this example, the equations determined by Jake and Jill were identical, except of course for rounding. Okay, so if you look, they don't look exactly identical, right? This one right here has 1.05 t, and on the previous page we have pi over 3 t, right? If you calculate that to a decimal though, pi divided by 3, it is 1.05. So they are the exact same equation. Okay, one is just written, this one here is just written and calculated to the nearest hundredth instead of left with pi in it. Okay. So this note just says the two boys got the exact same equations except for rounding, because all the data points that Jill used were on the graph of the function. But normally that's not the case, because remember, when you do a regression equation, it's not a perfect fit for the data. Most of the time when you do an example involving regression, you're looking for an equation that is the best fit for that. So you're looking for the line of best fit, generally, okay? Okay, one more example I just want to show you really quickly. This one is dealing with, again, like I said, the tides that come in, the depth of the water also can be modeled by a sine function or a periodic function. And so this just says the depth, d, in meters of water in a harbor t hours after midnight can be approximated by a sine function, and it's in this form where it tells you the hours after midnight are from 0 to 24. Okay, now this is important, hours after midnight. Okay. Oh, okay. And then the question says, state the amplitude and the equation of the midline, and from that information determine the maximum and minimum depths of the water in the harbor. Well, right now, when I look at this equation, it's kind of in mixed up order, isn't it? I know this is not the standard form, so the very first thing I would do is rearrange this equation so that it is in standard form. So we need to see 5 sine 0.524 t plus 1.571 bracket, and then that plus 12 at the end. Okay, because that plus 12 needs to be in its normal place when the equation is written in standard form, so that I can identify my A value, my B value, my C value, and my D value, right? Okay, so just make a note to yourself, rearrange if the equation is in the wrong way, in the wrong order, okay? Okay, so amplitude, A. Well, my A value in this equation is 5, so the amplitude is 5. My midline, that's really my D, okay? And I can read that right off the equation too. My midline is 12, okay? So then it says from that we can determine the maximum and the minimum depths of water in the harbor. Okay, well, if my amplitude is 5, normally my minimum would have been -5 and my maximum would have been +5. But if I have shifted this whole graph up 12, then that means my -5 is now at, I'm giving you a minute to figure it out, -5 plus 12 should be at 7. And my maximum value, which was at 5, is now shifted up 12. It should be at 17. So that makes my range from 7 to 17. This is my minimum, and this is my maximum. Right? Okay, determine the period of the function to the nearest tenth of an hour. This is really important to pay attention to, girls. When it says to the nearest tenth or to the nearest hundredth, make sure you really pay attention to that, okay? So period. Well, I don't know period, but I have my B value here, and I know B affects my period. So period is, what is the period of a normal sine function usually? 2 pi over my B, 0.524. Well, I'm just going to actually round that then, because it wants it to the nearest tenth. So I'm going to round that by 0.5 instead of 0.524, okay? And 2 divided by 0.5 is actually 4. So to the nearest tenth of an hour, it would be 4.0, right? Okay, and that's pi. So 4 pi is my period, okay? Now we need to figure out, if we were going to graph this equation, and they've given us the equation here, we don't even have to come up with it, we need to figure out what a suitable window would be. Okay, so it's telling us, let's see, so for our x's, which technically, that's your time, right, in this equation, your x's are time, would be on your x-axis, okay? And it's telling us here that our range for our time, or for our x-axis, is from 0 to 24. So that's what you would set for your window. You would say, I need to go from 0 to 24, and probably you could go up by 1s or 2s. These will vary a little bit. There's no just one right answer for these, but you just have to pay attention to what your domain would be, right? And then your y, well, let's see. Our maximum point and our minimum point will help us figure out what our range would be. We're going from 7 to 17, so I'd go a little above and a little below that, so maybe 0 to 20, and you could probably go up by 5s or 2s or something like that. Okay? Okay, then it says, use the graph of the function to determine some information. Well, we haven't even put this into our calculator yet, so we better do that. Let's go into our y1. You do this on yours as well. Okay, we're going to put this graph in, but I'm going to put in the rearranged version, my blue writing here, okay, so that it's in the form that I'm used to seeing, okay? So this will be y equals 5 sine, and then the bracket, 0.524, t, I'm going to use x because I don't really have a t there, plus 1.571. And then close your bracket, plus 12. Okay, you need to go in and make sure, though, that your window is set correctly for the windows that we've identified here. We have a x minimum at 0 to 24. We're going to go up by 2's. And then our y's, we're going to go 0 to 20. And again, we're going to go up by 5's this time. Okay? And when I graph that, okay, I hope that you're seeing the same window that I am. Okay, and the question says now, use the graph of the function to determine to the nearest tenth of a meter the depth of water at 2 o'clock p.m. Okay, we have to pay attention to that because our time, this 0 to 24 on our x-axis here, represents the hours after midnight, okay? So this will not be at the 2 here, at this 2, because that's 2 o'clock a.m. That's 2 hours after midnight. How many hours after midnight is 2 o'clock p.m.? We're going to have to count. Okay, so 12 hours after midnight would be 12 o'clock noon, and then 2 more hours beyond that. So this is 14 hours after midnight. Okay, so what we're trying to calculate is at 14 hours after midnight, that's what our x is going to be, right? Okay, so we're going to have to go second. We want to calculate a value when x is 14 hours after midnight. And if you do that, second, calculate a value when x is 14, it tells you that your y is 14.5, okay? And that's to the nearest tenth of a meter, okay? So your units are meters. Now, this is an interesting question because it says a ship that requires a minimum of 8.5 meters of water is in harbor at midnight. By what time to the nearest 10 minutes must it leave in order to prevent grounding? Okay, what I would like you to do is we're just going to sketch a quick sketch over here of what we have going on in this situation, okay? So we have our boat, and it had a ship that is in the harbor, okay? And mark on here, you have 7 as your minimum, and it goes up to 17 as its maximum, okay? And so this ship is going down to its minimum, or the waves, I guess, the tide is going down to a minimum of 7 and up to a maximum of 17, okay? But it tells us that this ship requires a minimum of 8.5 meters of water in the harbor. So we need to figure out here at 8.5 meters of water, when, if this is our time in hours, and this is our distance in meters, we need to figure out when this point would happen right here on our x-axis, okay? What is the time there? Okay, so we're going to have to draw a horizontal line across this graph right at 8.5 so that we can see at what time the depth of water is at 8.5 meters. And then we're going to need to figure out that the coordinates of that point there and the coordinates of this point here, because during this time here where the waves drop below that 8.5 meters, that ship would be grounded, right? It would not be able to float. So that ship has to leave to prevent grounding before that happens, okay? So how would we draw that horizontal line across at 8.5 meters? I hope you said you would have to go in and enter that as your Y2, 8.5 meters. And if you graph that, you're going to get that horizontal line going across, okay? So the waves are at a high enough level above 8.5 meters for this whole first part of our graph, right? But at this point where they're only 8.5 meters because the tide is going out. At that point, that's where that ship would be grounded. We need to figure out that's an intersection point where those two graphs intersect. So second, calculate an intersection. Remember, you don't have to give it a left or a right bound point. You just ride your cursor around until you get very close to that spot. Try and land pretty much on top of it and hit enter 3 times. And when you do that, you're going to get that there's an intersection at that point. Okay, and that's at 4.47. So let's just make ourselves a note what we did here. Second, we calculated an intersection point and the intersection point was at 4.477. Okay, but this time is being measured in hours, right? So this is 4.477 hours. We need to figure out how many minutes that is, because we have to know by what time in minutes must it leave, okay? So I'm going to have to multiply this by 60 to figure out what this is in minutes, okay? 60 minutes in an hour, right? So 4.477 hours. Well, the 4 hours part is okay because that's going to be hours after midnight. So 4 hours after midnight is going to be at 4 something, but it's this minute part we need to figure out, right? So we need to figure out this 0.477, how much of an hour that is. So 0.477 times 60. So 0.477 times 60 is 28.62 minutes, okay? 28.62 minutes. Okay, so this is 4 hours, and this part, 28.62 minutes. Okay, now the problem is, and I think about this because this is in a story situation, in a context, I wouldn't just round like I normally do. Because if this ship waited, this would round up to, well, it says to the nearest 10 minutes. So this would round up to 30, right? That's the nearest 10 minutes. But if I wait till 4:30, if at this point, 28.62 minutes, that water level's at 8.5 meters. Anything beyond that, so at 30 minutes, it's too late. We're right there, right? And that ship would be grounded because the water level is below 8.5 meters at that point, okay? So I can't go 4:30. I have to go to the 10 minutes previous to that. So instead of 4:30, it has to be 4:20. That ship would have to leave in order to prevent grounding, okay? So just make yourself a note here. 4:30 would be too late. The ship would be grounded by 4:30. So you have to round, instead of rounding up to 4:30 like you would normally, you actually have to round down 10 minutes. Okay. An interesting question. So the ship must leave by 4:20 a.m. or it will be too late. Okay? So this whole time in this section here, from here to here, while these waves are below 8.5 meters, that ship would be grounded. The next question says, what is the next time to the nearest necessary 10 minutes that that ship can safely return to the harbor? Okay, well, the ship can safely return anytime the waves are up here, right? Above 8.5 meters. Okay, so that's going to mean we need to find out this other intersection point. Okay, so go back to your graph, and we need to find out the second intersection point. So second, calculate an intersection, and ride it around again. Ooh. And try and get as close to on it as you can, and hit enter 3 times. And it will tell you that intersection point is at 7.513 if you rounded it. Okay, so second, calculate intersection, and it was at 7.513. And again, that's measuring in hours. We need to know what is the next time, not how many hours after midnight, but what is the next time. Okay, so it's going to be 7 hours after midnight and 0.513 hours, which we need to figure out how many seconds is that, so, or sorry, minutes is that. So we have to multiply by 60 to figure out the minutes. So 0.513 times 60 equals 30 minutes and 30.78 minutes. Okay, so let's see. 7:30 and a little bit more. 7:30 and a little bit more is this intersection point right here. So the ship can safely enter just past that, right? If this is 30.78, this is 7:30 and a little bit more, it would be grounded. So the next 10 minutes after that would actually be 7:40, right? Because we can't round down. Normally we would say, well, that would round to 30 minutes to the nearest 10 minutes, right? But we can't because 7:30 and just a hair more is this point where the waves are just at 8.5 meters. Okay, so in order for the ship to come safely back in, this time we're going to have to round up 10 minutes. Okay, these questions can be a little bit tricky because you really have to take the context into account when you're trying to figure out, would I round it up or would I round it down? It doesn't necessarily follow regular rounding rules, right? And when we're rounding to the nearest 10 minutes, it's a little different, right? This one would normally round to 7:30 to the nearest 10 minutes, right? 30 minutes. But at 7:30, we're here. At 7:30.78, we're here, right? And so that's why it's only safe for the ship here in this part above 8.5 meters in water depth, right? And so 7:30 is here. This is 7:30 and a little bit more, 0.78 minutes more, or 0.78 of a minute more, I mean. So we're going to have to round up. The ship can safely come back at 7:40. Okay, so you can see how there are many different ways to solve these equations. You can do a sinusoidal regression on them. You can use what you know about finding amplitude, midlines, periods, and the b-value to come up with the equation yourself. But either way, you're going to enter the equation into your calculator. You're going to use the graphing features of your calculator to answer and solve the questions. And you have to use some common sense because the stories are contextual. So there is an assignment that you're going to do in your book that goes along with this, but it's actually not the next few pages. You're going to skip right over to page 60. So just flip right through these examples, because really all of the examples are all very similar, and you're going to go right to page 60. This is what it looks like, and this is the review assignment, all about sine and cosine functions. Okay, there is an answer key at the back of the booklet, and the worked out answers and solutions will be on the website too, so if you get stuck, please look there. Some of the questions are really straightforward and very easy. Others take a little bit of figuring and a little bit of thinking and are a little bit more tricky. So do your best with them. See if you can find time to do those before class on Monday.